Hi everybody, Mrs. Pesek here. We are looking at section 1.9, inverse functions. You should each have a 1.9 gift, and that's really a notes gift. So you can just take notes on that gift and do the problems along with me. Your learning objectives in this section are to find inverse functions informally and verify that two functions are inverses of each other. Use graphs of functions to determine whether functions have inverse functions. Use the horizontal line test to determine if functions are one-to-one, and find inverse functions algebraically. So let's take a look. First of all, an example. Let's say that you have a part-time job, and let's say that you make, let's say $10 an hour. All right, so if I enter into like a little function machine the hours that you work, so let's say, I work for, 12 hours, and then my function machine is going to do something, and then my output is going to be the money earned. Well, if I earn $10 an hour, hopefully you understand that that function would be take the number of hours that you worked, and let's just say, we're going to enter, X for the hours that we work, okay? And then the output would be 10 times X would be the money that we earn. That's if the pay is $10 an hour. All right, so now if that's our output is 10X, then what if you're saving for prom or for a car or something like that, and you want to know how much money you need to earn, you want to know how many hours you need to work to earn that money. So let's say you're trying to save, $500 for something special. Then to figure out how many hours you'd work, you're going to enter the money that you want to earn or the money that you earned, and this time we're going this direction and we're going to make an inverse function, and we denote that like this with a little -1 after the F. And so then we want our output to be how many hours we would need to work. So the inverse function in this case is going to be take that total money earned, let's say we're entering X for that, and we're going to have to divide by 10. Take the total money we earn, divide by 10, and we'll get the hours that we work or will work to get that money. So in other words, in that case, if we enter $500, we're trying to earn $500, 500 divided by 10 is 50. So we would have to work 50 hours to make that much money. Okay, so let's take a look at this example. If f of x is equal to 3x, and I am explicitly defining that the domain is just 1, 2, and 3, then our range would be what? Well, if I plug in 1, I would get 3. If I plug in 2, I would get 6. And if I plug in 3, I will get 9. So my range would be 3, 6, and 9. So what is the inverse operation of multiplying by 3? Well, I'm hoping that you understand that the inverse operation of multiplying by 3 would be dividing by 3. Or you could say, I want to multiply by 1/3. That would be the same thing as dividing by 3. Okay, so if we interchange the coordinates, we will get the inverse function. All right, so if this is our input, let me back up. So in other words, we have these ordered pairs. We have 1 goes to 3, 2 goes to 6, and 3 goes to 9. But if we interchange those ordered pairs, we'll have 9 goes to 3, 6 goes to 2, and 3 goes to 1. All right, that's going to be all the ordered pairs that are on the inverse function, and our inverse function will just look like this. F inverse of x is how we read that, and it will just be x over 3. So if I enter a 9 and I take 1/3 of that, I get 3. If I take 6, 1/3 of that is going to be 2, and so on. I want you to notice now what's the domain of this new inverse function. Well, the domain is going to be all these x values. So 9, 6, and 3 is going to be our domain, and our range is going to be all of these y values. So 3, 2, and 1. 3, 2, and 1. So what I want you to notice is that in our original function, the domain was 1, 2, and 3. But in our inverse function, the range is 1, 2, and 3. Notice that the range of our original function was, actually lost it, range of our original function was 3, 6, and 9, and that has now become the domain of my inverse function. All right, so that the domain, so this is our note here, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Okay, so basically f and its inverse, a function and its inverse, undo each other. All right, so if I have f of x equals 3x, and f inverse of x is equal to x over 3, they're going to undo each other. It's kind of like I'm thinking of a number, I'm going to multiply by 3, but then I'm going to divide by 3. Won't I just get back to the original number? They're going to undo each other. So if I want to find f of f inverse, you know all about composite functions from section 1.8. So if I do f of, my inverse is x over 3, and so I'm going to plug in x over 3 into my f function wherever I see an x, like right there. So I'm going to have 3 times the x over 3, and the 3's divide out, and I'm just left with x. So I'm starting with x, and I'm ending with x. They're undoing each other. Let's test this for f inverse of f of x. So that means I want f inverse of, my f of x function was 3x. And now I'm going to go to my inverse function, and I'm going to plug in a 3x wherever I see an x, which would be right up here. So I'm going to have 3x over x. I'm sorry, 3x over 3. So now the 3's are going to divide out, and again, I'm just left with x. All right, so that brings up this definition. If f and g are two functions such that f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of f, then f and g are inverse functions. So if you take the composite of f of g and g of f, and they're both equal to x, then those two functions are inverses of each other, and that function g could be denoted as f inverse. Okay, so f of f inverse of x is always going to equal f inverse of f of x, and they're both always going to equal x. Note, the f with the little -1 of x means the inverse of f. It does not mean the reciprocal. So we're not talking about 1 over f of x. That is not what we're talking about. Okay, we're talking about inverse functions, not reciprocal functions. Okay, so let's test this out. Which of these functions is the inverse of f of x equaling 7x plus 4? So if I want to find the inverse of that function, then I'm going to test, you know, is it g? Maybe g is the inverse. Well, if it is, then f of g of x is going to equal what? We can simplify it, and if it's equal to x, then that'll be our winner. All right, so let's get rid of that, and let's test this out. So I want to find f of, and my g of x function is right here. It's x minus 7 over 4. And now I need to plug that function into the f function right here where I see an x. So I want 7 times x minus 7 over 4 plus 4. Well, if I simplify this, I'm going to get, you know, let's see, so the 7 and 4 don't divide out. I get like 7x minus 49 over 4 plus 4. I don't think that's equal to x. So I don't think this is our inverse function. Let's try f of h. Maybe h is the inverse. So let's do f of h of x. And so I'm going to do f of x minus 4 over 7. So I'm going to plug x minus 4 over 7 right here for that x. So I'm going to write 7 times x minus 4 over 7 plus 4. Now, in order to simplify this, we're going to have to show what can be done first. And the first thing that we can do here is we could divide this 7 out with this 7. But that's going to leave us with x minus 4 plus 4. Now, as our second step, we're going to show that the 4's subtract off. So I am indeed left with x. Now we need to show it the other way also. So it works for f of h of x. Let's see, does it work for h of f of x? That would be h of, what was our f function? It was 7x plus 4. And now I'm going to plug in 7x plus 4 in right here for this x in my h of x function. So I'm going to have 7x plus 4 minus this 4 over 7. Again, I need to show step by step how I can simplify this. All right, and so in this case, I would subtract off the 4's first. I'm left with 7x over 7, and now I can divide out the 7's, and I am indeed left with x also. So what did we just learn? We learned that f of h of x is equal to x, and h of f of x is also equal to x, and that result means that f and h are inverses of each other. And that means that we could write h, we really could write h as f inverse. So instead of writing h of x, we could write f inverse of x. So we found the inverse function. It was the h of x function. All right, so let's graph. Let's graph these two functions. We said that f of x was 7x plus 4, and the h of x function was x minus 4 over 7. And let's see what happens when we graph these. So if I'm going to graph this first one, I'll graph this one like this. The y-intercept is 4. The slope is 7. So I got to go up 1, 2, 3, 4, 5, 6. I'm a little bit off my graph. I'm about up here. And then down 7 and to left 1, 1, 2, 3, 4, 5, 6, 7 to left 1. So that line is looking something like, if I can get my line graph going here, it looks something like this. Okay, and let's see if I can move this a tiny bit over. All right, so there's our first graph. And then if I graph our second function here, this one, really, I might just plot some points for this one. Like if I plug in, this is x versus f inverse of x, I might plug in 4 for x. So if I plug in 4, I get 4 minus 4 is 0 over 7, so I get 0. If I plug in, what might be another good one? How about if I plug in 11? 11 minus 4 is 7, and 7 over 7 is 1. So that's a couple ordered pairs that I could plot. And how about if I plot like -3? If I plot a -3, if I get -3 minus 4, that's a -7. And -7 over 7 is a -1. So let me plot these 3 ordered pairs that we found. There's 4, whoopsie, 4, 0 is right here. Get rid of that guy. And let's see, that's 4, 0. I need 11, 1. That's a little bit off my graph, but it's about here. And then -3, 1, 2, 3, -3, -1. So here's our inverse function graphed. And so when I graph this and I draw my line through these points, it looks like this. All right. And try to get this to rotate slightly. It's not cooperating. There it goes. Okay. And so here's what I want you to notice about these two functions. So this function is my f of x function, and this function is my f inverse of x function. But what's really cool about this is that these functions are reflections of each other over a special line, and that line is the line y equals x. So let me get this going here. Y equals x is this line that goes from, you know, like -1, -1 to 2, 2 to 5, 5. You know, that would be the line. And so in this case, let me see if I can get this to go a little further up. So something like this. So they're mirror images over that line. And that's always going to happen when you graph functions and their inverses. They will always be mirror images over that line y equals x. That's the line y equals x. Okay, so let's practice graphing a few more inverse functions. So sketch the graphs of the inverse functions f of x equaling x squared plus 1, but this function has an explicitly defined domain of we just want x greater than or equal to 0. So if I'm graphing that original function, it's just the x squared function, which you know what that looks like, a parabola shape, but it is shifted up, 1 unit. So let's get some more accurate points than my quick ballpark graph there. So it's going to go through 0, 0, 1, 2. Instead of 2, 4, we're going to be at 2, 5, and so on. It'll go through -1, 2, and -2, 5. So the graph is going to look like this. However, we don't want the whole graph. We only want it graphed for x. That's not what I wanted to do. Let me try this again. Highlighter. There we go. We only want to see a graph for x greater than 0. So in that case, we are going to, let's get rid of this part. We only want to graph it from 0 and over. All right, so if I just graph that much, that's my f of x function, and my inverse function, that's this one, is square root of x minus 1. Well, you know what the square root graph looks like. It goes through 0, 0, 1, 1, 4, 2, 9, 3. It looks like this. But this graph has been shifted 1 unit to the right. So let's shift that graph over if we can. So it's going to look like that. I'll move those points over along with it. And so there's our inverse function. And again, these two functions, and this is my original graph here. This is the f of x graph. This is the f inverse of x graph. But they're both mirror images over that line y equals x. And that line y equals x looks something like, find it here, looks like this. So these two lines are mirror images over that line, y equals x. Okay, so that brings up something called the horizontal line test. The horizontal line test is a test to let you find out whether a function's inverse will also be a function. So a function f has an inverse function if and only if no horizontal line intersects the graph of the function f at more than 1 point. So that's our horizontal line test. If no horizontal line intersects function f at more than 1 point, then no y value is going to be matched with more than one x value, and this makes f a one-to-one function. So going back, let's see, do I have an example here? Let's see, let's go back to this graph that we did here. If I was to go back and sketch this whole function of x squared plus 1 and forget about this, this highlighted area, like, oh, we're going to have x just be greater than or equal to 0. So if that was gone and we did not have it, then we would have this whole graph. But that means if I look at some ordered pairs on there, I would have ordered pairs like, -1, x, y, I have -1 goes to 2, and +1 goes to 2. I would have one y value going to 2 different x values. All right, and if that's the case, then that means that function's not going to have an inverse. So a one-to-one function is going to be a function if each, so let me start again. A function is one-to-one if each value of the dependent variable corresponds to exactly one value of its independent variable. And that's not the case in our example here, because I've got one dependent variable value, like 2, and it's going to 2 different independent values of -1 and +2. So this function would not be a one-to-one. Oopsie. This function here would not be a one-to-one function. But if we limit it so the domain is just greater than or equal to 0, then it is going to be a one-to-one function. All right, let's see, go back for a second. All right, so a function f has an inverse if and only if the function is a one-to-one function. All right, so I'm going to skip that. So will the function graphed have an inverse? So let's take a look at these examples. So we're going to apply the horizontal line test. So if I draw a horizontal line through this function, will it cross through the function in more than one point? Well, yeah, it's crossing here and it's crossing here. That means this function will, well, it will have an inverse, but the inverse will not be a function. All right, so will the function graph have an inverse, or will it have an inverse function, I should ask? And the answer to this one is no. If I take my horizontal line and I try this function, well, now the horizontal line goes through at most one point, so that means that this is a yes, this function's inverse will be a function. How about if I try this one? Well, this one, if I draw a horizontal line through this function, it's going to go through more than one point, so that's going to be a no. Its inverse will not be a function. How about this? Whoopsie. How about this function here? This is our square root graph, and that looks like it will have an inverse, so its function will have an inverse function. And so in this case, I'm going to say that's a yes. And one last one, how about this kind of a polynomial shaped graph? This is going to be a no. The inverse of this is not a function, and that's because that horizontal line goes through more than one point. So whenever I said yes, that function is a one-to-one function. So that one's a one-to-one function, that one's a one-to-one function. The other three are not one-to-one functions, and their inverse will not be a function. Okay, so let's take a look at steps for finding an inverse function. So if we're going to find an inverse function algebraically, we're going to follow these steps. All right, and let's see, I'm going to see if I can shrink this down so we can see all these steps. Okay, so for this, we're looking at the steps for finding an inverse function. So first of all, you would use the horizontal line test to determine if an inverse even exists. All right. So, you know, if we were going to say, oh, let's find the inverse of, let's just make up a function right now. Let's say I was going to try and find the inverse of f of x equaling, you know, 3x minus 5. All right, well, I could graph 3x minus 5 on my calculator, but that's just going to be a line. It's going to look something like this, and it's going to pass the horizontal line test, so it's all good. So now we're on to step 2. It says rewrite your f of x as a y. So we're going to write y equals 3x minus 5. Now we're on to step 3. Step 3 says switch the x and the y. So I'm going to write x equals 3y minus 5. Now we're on to step 4, and step 4 says solve for y. So if I'm going to solve this equation for y, I'm probably going to need to add 5 to both sides. So I get x plus 5. By the way, I probably didn't leave you any room for this example, so hopefully you're putting this example on a separate sheet of note paper. So I get x plus 5 equals 3y. And then if I divide both sides by 3, I would get y equals x plus 5 over 3. Now we're on to the next part, which is replace y with f inverse in your new equation. So in that case, I'm going to rewrite this as f inverse of x equals x plus 5 over 3. All right, and now we are on to verifying. So verify that f and f inverse are inverses, are inverse functions, by showing that the domain of f is equal to the range of f inverse and that the range of f is equal to the domain of f inverse. Well, for this particular problem, that's not really a very interesting point. So for this one, that's not all that interesting to talk about because, you know, the domain for f and for f inverse is all real numbers. So the domain of the original function has to become the range of the inverse and vice versa, but they're all going to be negative infinity to positive infinity. So let's just move on to this last part then, which says show that f of f inverse is equal to x and f inverse of f of x is equal to x. All right, and so with that, that means that we are going to use our composite function skills again, and we're going to do, let's see, let me write off my functions again. F of x equals, what was my original function? It was 3x minus 5. All right, so here's my f of x, and here's my inverse that I just found, and now we're going to verify that this works. So we get f of x equaling, I'm sorry, let's see, let's back up. I want f of f inverse of x, and I want to show that that's equal to x. So I'm going to plug in my inverse function, which we said was x plus 5 over 3. That's supposed to be a 3. And then let's see what we get. We're going to get, I got to plug that in right here where the x is. So I'm going to get 3 times x plus 5 over 3 minus 5. And again, we're going to show step by step what happens. This 3 can divide out with this 3. So we get x plus 5 minus 5. And then we show that these 5 subtract off, so we get x. If you try and do both those steps at the same time, I'm going to have to mark it wrong. So make sure you show step by step, one step at a time, what you get. All right, so you have this example on your gift. So you can go ahead and do that on your own. So that one will be a similar problem to what we just did together. But you know what? We never tested it the other way. Whoopsie. We never tested it the other way. So let's do that. That means we need to test f inverse of f of x. So that's going to be f inverse of, and we said our f of x function is 3x minus 5. And that means I'm going to go into my inverse function and plug in 3x minus 5 right here where that x is. So I'm going to get 3x minus 5 and then plus 5 over 3. And for this one, I cannot divide out the 3's first. Instead, I would have to subtract off the 5's first and get 3x over 3 and then divide out the 3's and show that that's equal to x. So we showed that f of f inverse of x is equal to x and f inverse of f of x is equal to x. So now I feel good that these two functions that I circled here, this one, fx equaling 3x minus 5, and this one, x plus 5 over 3, are inverse functions. All right, so again, I'm having you try this one on the gift on your own. Okay, let's test this one. Find the inverse of f of x equaling square root of 10 plus x. For this one, again, the steps, I would graph this on a calculator maybe to see what the graph is, but this is really draw this here. This is really our square root function that looks like this, except x plus 10 looks like it's be shifted to the left 10 units. So it would look something like that. Is that graph going to pass a horizontal line test? Yes, it will. So now we can go on and find the inverse and the steps again. If I can remind you, the steps are you rewrite f of x as y, and then you switch your x and your y, and then you solve for y. So in order to solve for y here, I think I would have to square both sides of this equation. So I get x squared equaling square rooting, and the squaring are canceling each other out. So I get x squared equals 10 plus y. And then my last step would be to subtract 10 from both sides. So I would get y equals x squared minus 10. And then if I rewrite y as f inverse of x, I would get x squared minus 10. Now, hold up for a minute because we have a little thing to discuss, and that's the domain and range. It's causing a little bit of a problem. So let's talk about the domain for this original function. The domain for our f of x function, we can't have any negatives under there, so 10 plus x has to be greater than or equal to 0. Let me do that off to the side here. And if I subtract 10, I get x is greater than or equal to negative 10, which means my domain is negative 10 to positive infinity. I'll write that right here, negative 10, positive infinity. And what about the range? Well, the range is still just 0 to positive infinity. We have not shifted up or down or anything like that. So my range is going to be negative infinity to positive infinity. All right, now remember that these two, kind of highlight these if I can. No, it's not going to let me. There we go. Grouping, 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 grouping. Okay, so that was the domain and the range for my original, but I'm going to kind of hold these down here and put them here. So now if I'm trying to find the domain and range for my inverse function, remember that the domain of the original has to become the range of the inverse, and the range of the original has to become the domain of the inverse. And so in this case, my domain has to be negative infinity to positive infinity, but my range is only going to be negative 10 to positive infinity. All right, so wait a second. I think I messed up. Where did I mess up? Oh yeah, I did. So my humblest apologies. You're probably like, well, so let's take a look at the graph of this. I'm going to graph my original. I know exactly what I did wrong, so let's fix it. Maybe you do too. So if I'm going to my graphing page and I'm going to do a graph, and I'm going to type in my parent function, which was square root of 10 plus x. There's that function. It's starting at negative 10, 0, and going up and to the right. So the domain is negative 10 to positive infinity, but the range is 0 to positive infinity. And I feel like I might have said that, but I wrote negative infinity to positive infinity. So I apologize for the blunder. So let's fix this with my eraser. So this, I got to fix this right here. My range is how far down does the original function go, how far up does it go, and again we see it just going from a range of 0 up to positive infinity. So this should be, let's fill this in here, this should be this should be 0 to positive infinity. So fixing this up, that means I got to erase this, fix this up. This domain of my inverse should be, I've got to erase this too, because our domain of this should be 0 to positive infinity. So that means when I want to graph this function right here, this inverse function, you know, normally I'd be, oh, it's x squared graph. It looks like this. And wait, I just want to shift it down 10, so it should, you know, it should look something like this. But according to this domain here, right, according to this domain, I can only have this graph from 0 to positive infinity, which means I really need to erase part of this graph. I just want to get rid of all of this and really have my graph just from just from 0 to positive infinity. So my graph is really going to look something like this. So my original function, and I guess I had my graph over here. So my original function I graphed here like this, and here's my new one that's like right around here. And let me get rid of my little line here that I was using to test to see whether it was a one-to-one function. And here, these two functions are going to be mirror images over the line y equals x. All right, and it's a beautiful thing. Okay, so that's that example. What if we wanted to find the inverse of f of x equaling x minus 4 over x plus 9? This one is a little trickier, so let's do this one together. For this one, and again, you might have to be doing these extra examples on a piece of notebook paper. Find the inverse of f of x equaling x minus 4 over x plus 9. We start by, rewriting f of x as y. So I get y equals x minus 4 over x plus 9. By the way, we could graph this to make sure it's going to be a one-to-one function. So, you know, why bother trying to find an inverse if it's not going to be a function? So if I do x minus 4 over x minus 9, I'm going to add a new page to this document, new graphs page, and control divided by, and I wanted x minus 4 over x plus 9. I believe that was what it was, yep. And so that's what the graph is looking like, except I don't think we're looking high enough here, so I think let's make this like 25. Oh, I'm seeing something over here to the graph. Let's make this like a negative 40. So the graph is expanding here, make this like 40. So our graph is looking something like this. If I expand out a little bit, does this graph pass a horizontal line test? It does. Any horizontal line I draw will go through this graph in at most 1 point. So we're going to try and find the inverse of this. And remember, the inverse should be the mirror image over the line y equals x. So how do we find it? So we start by rewriting f of x as y. And then we're going to rewrite, well, no, we're going to switch all the x's and y's. So I'm going to write x equals y minus 4 over y plus 9. And now I would try to get rid of that denominator. So let's multiply both sides by the quantity y plus 9. So on the left side, if I distribute, I'm going to get xy plus 9x. And on the right side, the y plus 9s are dividing out, so I'm left with y minus 4. Now we're trying to solve for y, and I see y in a couple places. I see y here, and I see y here. So I think the best thing for us to do would be to get the y's together, any term with a y in it, on the same side. So let's subtract y from both sides. So I get xy minus y. And let's subtract 9x from both sides. Let's get the non-y terms on the other side. So I've got xy minus y equaling negative 4 minus 9x. And so in this case, I now see that I've got the y's on one side and the terms without a y on the other side. But we only want to see y written once, and I'm still seeing y written in two different terms. So one way to get y to be written just once is to factor out the y. So if I factor out a y, I get y times x minus 1. Now I only see y written once, and that's equal to negative 4 minus 9x. And so now the last step to get y by itself, we're almost there, is to divide both sides by x minus 1. And so now we can write our, these are dividing out, and so now we can write our inverse function as negative 4 minus 9x over x minus 1. So that's our inverse function. And let's test this on our calculator and see if it really looks like the two functions are mirror images of each other over y equals x. So I'm doing negative 4 minus 9x. Let's see, I'm going to push tab, and I'm going to do control doc. And I think I said negative 4 minus 9x over, let's see, negative 4 minus 9x over x minus 1. And there is my new graph. And let's just type in the line y equals x just to see what that looks like. All I have to do is say f4 of x equals x for my example. And sure enough, I think that these two functions look like they are mirror images over that line y equals x. All right, and that's it for this video. Thanks for watching.